Exercise 27 corresponds to this 8.4.1. An AB category, recall this means a preadditive category or z-linear category. It's the same thing with different terminology. So recall this means the home set is a group, and moreover the composition of homomorphism satisfies certain rules, which means compatible with the structure, the group structure of the home set, which means if you have J composed with H1 plus H2 to homomorphism, it equals J composed H1 plus J composed H2, and the addition is the addition structure of the abelian group home set as this emoji. Okay, so then the category is furthermore called additive category if it has zero object and finite product, or just product of pairs. It's enough to tell you it also has finite products. And in this case, finite products will be the same as finite coproducts. And it is traditional, conventionally, to just write A direct sum with B to represent either the product or coproduct. This is the additive category, and one step further, you got abelian category, which is additive category satisfies three more conditions. So the first two is labeled by AB1 and AB2. Okay. So AB1 is every map has a kernel and co-kernel. Secondly, every monic is a kernel of its co-kernel, and thirdly, every co-kernel, every epimorphism is a co-kernel of its kernel. This will furthermore imply that monic equals kernel and epi equals co-kernel in abelian category, because monic is a kernel of co-kernel. Conversely, every kernel of co-kernel is morphism, is a monic morphism, and so monic is equivalent to being a kernel. And the same for epimorphism. Okay, so the exercise asks you to prove a morphism in AB category is monic if and only for every non-zero morphism the composition gives you non-zero. This epimorphism for every non-zero homomorphism the composition gives you non-zero. Of course, the composition the different side. Okay, this is very direct. Just recall the definition. So let's first prove one. If F is monic, if and only if its composition is non-zero is non-zero. So suppose F is monic, then F composed with a non-zero. Suppose it's zero. Let's prove by absurd. Then by the monicness, F composed E equals 0 implies F composed E equals F composed with 0. And so the monicness would tell you that E equals 0, but this is contradicting the fact that EA is not a zero morphism in the home set, not a zero element. Secondly, suppose you have F composed non-zero is non-zero. Let's prove it is monic. By definition, mean that suppose you got F composed with G equals F composed with H. So for some G and H from some category D to B, and then you compose with the morphism F from B to C to form two different morphisms from D to C in priori, but suppose they are the same, then you want to show at the beginning they are the same. And this just comes from the fact this is AB category, and so you could, in particular the home set group, so you could applying the distributive law the home set, and this gives you F composed with G minus H equals 0, and F is monic tells you that G minus H is 0, which means G equals H. The similar proofs also works for the other the statement 2.